Okay, good morning class. So we'll start the class and I'll send you another link once this, it stops at 40 minutes because there was some problem with my GoToMeeting here. So that's why I've started with Zoom. Okay, so last class we saw about antacids. We saw the classification of antacids as two types based on the pharmacological action and based on the absorption. So we saw there were two types, absorbable antacids and non-absorbable antacids. They are also called as systemic antacids and non-systemic antacids. Systemic meaning they get absorbed into the blood circulation. Non-systemic meaning they don't enter into the blood circulation. Okay, so can you tell me where does the sodium bicarbonate come? Which type of an antacid is this? Is it a systemic antacid or is it a non-systemic antacid? Yes, anyone?
Systemic.
Yes, it is a systemic antacid. So, sodium bicarbonate, I am sure you must have all known this. It's given by the molecular formula NaHCO3. The molecular mass is 84.01 grams. It is also called, synonym means the other names. So the synonyms for sodium bicarbonate are baking soda, bread soda, cooking soda, bicarbonate of soda, or it is also just called as sodium hydrogen carbonate. As you can see in the molecular formula NaHCO3, right? It is also called as sodium hydrogen carbonate. Okay, so these are the synonyms for your sodium bicarbonate. Coming to the properties, let's look at the appearance. So the appearance of sodium bicarbonate is, it is white in color and it is a crystalline powder or granules. Coming to the odor or smell, it is odorless. That is, it has no smell. Taste, it has a salty taste. It is called as saline taste. Density is 1.1 to 1.3 gram. Okay. And the melting point is, it does not melt, but it decomposes to sodium carbonate, that is Na2CO3. It decomposes to sodium carbonate starting at 50 degree centigrade. Then when it comes to solubility, it is freely soluble in water. Now, if you look at this particular line, solubility in water, you will see that there are different temperatures which is mentioned. So at 0 degree centigrade, 69 grams of sodium bicarbonate can dissolve in 1 liter of water. So that is what it means, 69 grams per liter. Okay, that is at 0 degree centigrade. At room temperature, say 20 degrees centigrade, 96 grams can dissolve in 1 liter of water. When you heat it to 60 degrees centigrade, the solubility increases. It is 165 grams. And if you heat it to 100 degrees, then it further increases. It is 236 grams per liter. Okay. So this is how the solubility depends on the temperature. Coming to the refractive index property, the refractive index of sodium bicarbonate is 1.583. So next we'll move on to the preparation of sodium bicarbonate. So how is this sodium bicarbonate prepared? Now, sodium bicarbonate may be obtained by the reaction of carbon dioxide with an aqueous solution of sodium hydroxide. The initial reaction produces sodium carbonate. Further addition of carbon dioxide produces sodium bicarbonate. Okay, so as you can see in the synthesis of your sodium bicarbonate, the first step is the production of sodium carbonate. Okay, that sodium carbonate, on further addition of carbon dioxide, it produces your sodium bicarbonate. Okay, so when you are going to write preparation, you very well have to write the reactions as well. Okay, so the first step is CO2 plus NaOH to give you Na2CO3, that is your sodium carbonate plus water. Okay, this sodium carbonate further reacts with carbon dioxide plus water to give you your sodium bicarbonate. Okay, so this is one method of preparation, and this is usually done on a small scale preparation, you can say. So when it comes to industrial scale, now the difference is small scale means it is of a small quantity. Industrial scale means it is in bulk. You have to manufacture it in bulk. That is why it is called as an industrial scale. So on an industrial scale, it is obtained by a process called as Solvay process. So what is this Solvay process is? Brine solution, that is sodium chloride, is saturated with ammonia to remove traces of impurities like magnesium and iron. The solution is filtered and passed through a tower called as a carbonating tower. So in this, it is allowed to come in contact with a current of carbon dioxide, and the tower is cooled to enhance the precipitation. So this precipitate is filtered out and dried. So the precipitate that you get is your sodium bicarbonate. So this whole process is called as a Solvay process. So as you can see, there is carbon dioxide and water, which will give you your hydrogen carbonate, H2CO3. This further reacts with ammonia to give you your ammonium bicarbonate. Okay, so see, the difference that you should remember here is whenever the term bicarbonate comes, then it is HCO3. Okay, if it is carbonate, it is just CO3. Okay, so in the second reaction, under the second process of preparation, you can see ammonia reacts with hydrogen carbonate to give ammonium bicarbonate. This ammonium bicarbonate reacts with NaCl. Now NaCl is also called as brine. This reacts with your NaCl to give you your sodium bicarbonate along with a byproduct, that is your ammonium chloride. Okay, so this is the method of preparation of your sodium bicarbonate. Any doubts so far? Yes, any doubts?
No, ma'am.
No, ma'am.
No, ma'am.
Aisha, can you take the attendance? So coming to the assay of sodium bicarbonate. So how is this assay done? So assay is done by this method. How? You're going to weigh accurately 1 gram of sodium bicarbonate and dissolve it in 20 ml of water. This solution you're going to titrate with 0.5 normal sulfuric acid using an indicator called methyl orange. Okay, so it's a very simple procedure. There is no heating or there is no other steps which is involved. You're just going to dissolve sodium bicarbonate in water and you're going to titrate it against 0.5 normal sulfuric acid using an indicator called as methyl orange. See, now this explains the preparation by your Solvay process, I told you, right? So this is how the flow chart is. So you can see brine, which is also called as sodium chloride solution. Okay, it reacts with ammonia to give you your ammoniated brine. Okay, how is this ammonia got? Ammonia is got from your, okay, they have not shown how you have got ammonia, they've just shown the ammonia recovery. Okay, so ammonia reacts with your brine, that is NaCl, to give you ammoniated brine. This ammoniated brine is further taken into a tower called as carbonating tower, that is carbon dioxide is there in that tower. Okay, so this ammoniated brine reacts with your carbon dioxide to give you a product. Okay, so that product you're going to filter. Once you filter, you're going to get your sodium bicarbonate. Now, you can stop at this process if it is only sodium bicarbonate that you want. But if you want sodium carbonate, you have to heat it to 300 degrees centigrade, wherein the sodium bicarbonate decomposes. We saw, right, in the properties, sodium bicarbonate decomposes starting at 50 degrees centigrade into sodium carbonate. So if you want complete decomposition, then you have to heat it at 300 degrees centigrade to get your sodium carbonate. But anyhow, this is not what we want. We just want to stop it at sodium bicarbonate. So this is just a flow chart of the same thing which I explained. So next, coming to the reactions, okay? So thermal decomposition, we already saw this, right? Above 50 degrees centigrade, sodium bicarbonate gradually decomposes into sodium carbonate, water and carbon dioxide. But the conversion is fast at 200 degree centigrade. Next reaction is it reacts with acetic acid, producing sodium acetate, water and carbon dioxide. Then next one is it reacts with bases such as sodium hydroxide to form your carbonates. Okay. So if you treat it with sodium hydroxide, you're going to get your sodium carbonate. Last reaction is when mercury chloride solution, that is HgCl2. When mercury chloride solution is added to a solution of sodium bicarbonate, a reddish precipitate of mercuric oxide is formed. HgO is your mercuric oxide. Along with this, you do get your byproducts, that is your sodium chloride, water and carbon dioxide. Now this sodium chloride, though it is a solid, it will not precipitate because sodium chloride is very freely soluble in water. So that will remain in your solution, whereas the mercuric oxide will precipitate out as a precipitate. It will precipitate out because it is insoluble in water. Along with this, you also get carbon dioxide, which you will see as an effervescence. So these are the reactions of your sodium bicarbonate. Any doubts?
No, ma'am.
Okay, moving on. This is very important. What is the test for identification? That is, how are we going to identify that what we have prepared or what we have got in our lab is really sodium bicarbonate? Okay, so the test depends on either one test to just determine whether it is sodium bicarbonate or individual tests to determine whether the sodium ion and the bicarbonate ion is present or not. Okay, so the first test is to 5 ml of 5% solution of your sodium bicarbonate in carbon dioxide free water. Now, why should it be carbon dioxide free? Because you don't want it to further react to form your sodium carbonate. Okay, in carbon dioxide free water, add 0.1 ml of phenolphthalein solution. Okay, when you add this solution, a pale pink color is obtained. On heating, a gas is evolved and the solution turns red. Okay, so if you get this pale pink color and red color, then you can identify and say that yes, what I have is a sodium bicarbonate powder itself. Okay, so this is one test. The next tests are, they are broken down, wherein you're going to find out whether really it has sodium ion and whether really it has bicarbonate ion or whether does it have carbonate. So just to check this, you're going to do further tests. That these tests are called as confirmatory tests. You're going to find out whether really sodium and bicarbonate ions are present or not. So coming to the sodium ion, for sodium. So to sample solution, you're going to add 15% potassium carbonate solution and you're going to heat. So when you heat, no precipitate is obtained. So to this same solution, you're going to add potassium antimonide solution and you're going to heat it to boiling, cool, and if necessary, you're going to scratch the inside of the test tube with a glass rod. Once you do this, a dense white precipitate is produced. So if you get this precipitate, then it is confirmed that yes, sodium ion is present. Okay. So this first test is actually 2 steps. In the first step, you're just going to add potassium carbonate, heat, wherein you should not get any precipitate. But you're not going to discard that solution. You're going to continue into the next step. So wherein you're going to add potassium antimonide solution, heat, and then cool. Upon cooling only, you should get a dense white precipitate. But sometimes what happens, you need to initiate or you need to trigger the reaction. So in order to do that, that is why it is written, if necessary, scratch the inside of the test tube with a glass rod. So now this scratching, no, what happens is the glass rod acts as a catalyst, or it helps in speeding up the reaction. So by doing that scratching, a dense white precipitate is produced. Okay. If at all you don't get a dense white precipitate even after scratching, then it is confirmed that your compound does not have a sodium ion. Okay. So the second test for the sodium ion is acidify the sample solution. Now you have a sample solution of your sodium bicarbonate and you're going to acidify it with 1 molar acetic acid. Then you're going to add excess of magnesium uranyl acetate solution. Once you add this, if you get a yellow crystalline precipitate, then yes, sodium ion is present. If you don't get, then sodium ion is absent. I'm sure you must have all done these types of reaction, you know. I mean, you would have written in your observation book wherein you make 3 columns, test, observation, and inference. Have you all done this in your +2?
Yes,
Yes,
ma'am.
ma'am.
Yes, so this is what it is. So in the test column, you're just going to write acidify the sample solution with 1 molar acetic acid and add excess of magnesium uranyl acetate solution. In the observation column, you're going to write whether you get a precipitate or not. So if you get a yellow crystalline precipitate, in the inference column, you will write sodium ion is present. Okay. So this is how all these identification tests should be written. You know, it is a very neat way of dividing it into columns and saying, you know, that whether it is present or absent. Okay. Coming to test for identification for bicarbonate ion. So what you're going to do here is, to the sample, you're going to add magnesium sulfate. At that point, no precipitate is produced. So in inference, you're still not going to write anything because this is just part 1 of your first test. Part 2 is, on boiling, a white colored precipitate is formed. So if you do get a white colored precipitate, then you're going to write in the inference column that bicarbonate ion is present. Now, once you see that sodium ion is present and bicarbonate ion is present, and you do further confirmatory tests like by checking its melting point and the first test, that is the test for identification, you will finally write the result as the compound that I have got is sodium bicarbonate, which you can confirmatorily tell by doing all these tests for identification. So next, coming on, what are the uses? So now we already know, right, that it is a systemic antacid. Also, it is used in electrolyte replacement. Now, electrolytes are nothing but ions like sodium, potassium, chloride. Okay, so these are all your electrolytes, which is very much necessary for the functioning of your body. Sometimes there will be increase in levels or decrease in levels. So whenever there is a decrease in levels of your bicarbonate ion or sodium ion, you can use this sodium bicarbonate as an electrolyte replacement. Okay, so this is its another use. Coming to the next one, it is used as a systemic alkalizing agent used in the treatment of metabolic acidosis. So whenever there is, decrease in the pH, that is when you have acidity, you can use this in the treatment. That is, it will help in alkalizing the body's pH. So that is why it is called as a systemic alkalizing agent. Next, bicarbonate of soda can also be useful in removing splinters from the skin. Do you know what is called as splinters? Do you know what is splinters?
No, ma'am.
Okay, you very well know what it is. You just don't know the word that is used. Now, supposing, near the door, a little bit of wood has chipped out. Okay, and by mistake you have kept your hand there, and a little piece of wood goes into your skin, right? That is only called as splinters. Okay, so to remove the splinters also you can use this sodium bicarbonate. So when you put it, what will happen is it will liberate the skin, it will just cause the pores to open up, wherein it is very easy for you to remove the splinters. So for that also it can be used. The next use is it can be added to local anesthetics to speed up the onset of their effects and make their injection less painful. Any idea what is local anesthetic? You all know what is anesthetics, right? I'm sure you'll be having a little bit of idea as to what is anesthesia.
Yes, ma'am.
Okay, so anesthesia, in that there are two types, okay, which you will be studying further along. There is something called as local anesthesia and something called as general anesthesia. General means your whole body will be put into sleep. Local means only a particular part of the body wherein, the treatment or surgery has to be done. Only that part will be numbed. Okay, so sodium bicarbonate can be added to local anesthetics to speed up their effects and to make the injection less painful. Next, it may be used as a buffering agent, that is combined with table salt, that is sodium chloride, when creating a solution for your nasal irrigation. Next use is as a 0.1% to 1% solution. It can be used as an eye lotion. Then it can be used to remove ear wax and lubricating fluid for contact lenses. See, we were just thinking from the pharmaceutical point of view, right? As a systemic antacid, as an electrolyte replacement. But look at all the other uses also. Okay, we were just studying it under antacids, but we are seeing that apart from being an antacid, it also has many other uses. So it is also used to remove ear wax. Then it is used as a lubricating fluid for contact lenses. Next, 5% to 10% sodium bicarbonate solution is used as local applicants for burn, insect bites, etc. Last one is it is used in the preparation of your effervescent formulation. That is, if you put it into water, it helps in the evolution of your carbon dioxide. So therefore, it can be used in the preparation of your effervescent formulations as well. Okay. So these are the various uses of your sodium bicarbonate. So it may come as a 2 marks question. So wherein you have now, see, I've given you so many points. In this, if you write any four or five, it will be more than enough to fetch you 2 marks. So next we will see what is the side effects of sodium bicarbonate. So of course we all know one side effect. What is it? Main side effect is metabolic alkalosis. That is, if you take, because it is a systemic antacid, it enters into the blood circulation. Since it enters into the blood circulation, it will alter the pH of the blood. That is, it will increase the pH of the blood. See, you just wanted this sodium bicarbonate to increase the pH in your stomach. But since it gets absorbed into the blood, it will also increase the pH of your blood. So this is called as metabolic alkalosis. Now, because of this, there will be different more side effects. Okay, so this is one main side effect. And one more is high doses may cause headache, nausea, or irritability. So apart from metabolic alkalosis, there are few more side effects. That is edema due to sodium overload. Edema means inflammation. Then congestive heart failure. Then hyperosmolar syndrome. Hypervolemic hypernatremia. Hypernatremia means there is increase in your sodium ions. And hypertension due to increased sodium. Okay. So all of this you can see, because it gets absorbed into your systemic circulation as sodium ion and bicarbonate ion, it will increase the pH. Now, because there is more of sodium ion, it leads to hypervolemic hypernatremia and also hypertension. So therefore, this sodium bicarbonate, mainly due to its side effects, it is not used as an antacid anymore. Okay, but it is used for the other uses which we saw. Okay, so next is this. Okay, So next is the dose. So what is the dose of the sodium bicarbonate? So if at all there is no other option for you and you have to give sodium bicarbonate itself as an antacid, then you should know the dose. So the dose is 300 mg to 2 grams per day in divided dose. Divided dose meaning you're going to divide it. Now 300 mg, you're not going to take one time as 300 mg itself. Okay, so you may take it as 100 morning, afternoon and night, or you may take it as 150. That is 150 mg in the morning and 150 mg in the night. So that is what is called as divided dose, and this usually varies from patient to patient. So coming to the storage, storage is store in an airtight container. Okay, so with this we finish sodium bicarbonate. Any doubts? Anything that you want me to go over with this sodium bicarbonate?
No, ma'am.
Okay.
No, ma'am.
Okay, so we'll move on to the next one. So that is aluminium containing antacid. So aluminium containing antacid is widely used, okay, and it is a non-systemic antacid. See, under non-systemic antacids, we saw aluminium containing antacids, magnesium containing antacids, calcium containing antacids. So under this, first we will look into aluminium containing antacid, okay. It usually buffers in the pH range of 3 to 6, and it is constipating in action. So this is in general about your aluminium containing antacids. So we will look into there are two compounds which is there under your syllabus, that is aluminium hydroxide gel and aluminium phosphate. We'll try to finish those two today. So aluminium hydroxide is recognized by the United States Pharmacopoeia in two physical forms. One is aluminium hydroxide gel, okay. So this aluminium hydroxide gel is white in color, okay. It is a viscous suspension and it permits suitable flavoring and antimicrobial agents, okay. So since this is a syrup or a suspension, you can, the United States Pharmacopoeia permits to use suitable flavoring and antimicrobial agents, and the pH of this preparation, that is your aluminium hydroxide gel, is 5.5 to 8. So the second formulation under USP is dried aluminium hydroxide gel. So as the word says dried, it means to say it is a powder, okay. So it is not a gel. Though the name is there as dried aluminium hydroxide gel, because of the word dried, it is not a gel, but it is an amorphous powder. This is also white in color. It has no odor and it has no taste. Coming to the solubility, it is insoluble in water and alcohol, and it is soluble in dilute mineral acids and alkali hydroxides. So in this, we are going to just see with the aluminium hydroxide gel. So this is aluminium hydroxide gel. Aluminium hydroxide is given by the formula AlOH thrice. So as you can see, the aluminium group is bound with 3 OH minus ions. So the molecular mass of this is 78 grams. The synonyms for this is hydrated alumina, orthoaluminic acid, or aluminic acid. So in your questions, we may just tell you that write the uses of hydrated alumina. Then you should not be confused. Okay, what is this hydrated alumina? Ma'am did not teach it, no. Under aluminium containing antacids, she just taught two compounds, aluminium hydroxide and aluminium phosphate. From where did this hydrated alumina come? So synonyms are very important, because that is how they can twist and ask you the questions, either in your theory or also in your viva. Or they may ask you, just tell me the synonyms of aluminium hydroxide gel. So that is why synonyms are important. Okay. So it is found, aluminium hydroxide as such is found in nature as a mineral gibbsite, also known as hydrargillite. Okay, and its three much rarer polymorphs are barite, doylite, and norstrandite. Coming to the properties, we already saw It is a white amorphous powder. It is odorless. It is tasteless. The melting point is 300 degrees centigrade and the density is 2.42 grams. Coming to the solubility, it is practically insoluble in water and alcohol, but it is soluble in dilute mineral acid and in solution of alkali hydroxide. Coming to its chemical properties, it is amphoteric in nature. Amphoteric means it has both basic properties as well as acidic properties. So in the presence of an alkali or a base, it behaves as an acid. Okay. So in the presence of an alkali, it behaves as an acid. So AlOH3 will give you 3 hydrogen plus and AlO3 minus. Okay. So the next one is actually, they've given it wrong here. In the presence of an acid, it behaves as an alkali. Okay. So in the presence of H plus, it will give you OH minus plus Al3 plus. That is what it means. Okay. There is just that mistake. I will correct it and send it to you when I send you the PPT. Coming to its reaction, it reacts with acid and gives salt and water. That is AlOH3 reacts with acid, that is HCl, to give you a salt, that is aluminium chloride, AlCl3 plus water. Okay. So this is the properties, molecular formula and synonym of your aluminium hydroxide gel. So there is one more property of this aluminium hydroxide gel that is called as acid neutralization. So now what is this acid neutralization? It means to say, why are we first of all using this antacid? We are using this antacid because there is an excess of acid which is produced in the stomach. So when you're going to neutralize it, of course you have to neutralize it by substances which is alkaline in nature. So this property is called as acid neutralization. So how is this aluminium hydroxide helping in the acid neutralization? So you can see it in the reaction which is given below. That is AlOH thrice reacts with 3 molecules of water to give you a complex which is basic in nature. So the complex, you can see it is given by the molecular formula AlH2O thrice plus OH thrice. So this is the complex that is formed when your aluminium hydroxide reacts with water. Okay. Now this aluminium hydroxide is considered as an ideal antacid. Okay. It is soluble in acidic media and the overall mode of action is in a series of steps depending on the amount of antacid and the pH. Okay. So if you see, we saw the complex, right? Who is scribbling? Who is scribbling on this? Okay, fine. Moving on. Yeah, thank you for removing it, whoever it was. So the complex is soluble in acid media. So you saw the complex, right? We saw AlH2O thrice plus OH thrice. This is the complex which is basic in nature. That is why it is written as base. So this base reacts with acid. So the acid here is H3O plus. Okay. It reacts with this to give you 2 products, that is conjugated acid and conjugated base. Now conjugated acid, what happens? You can see here, it becomes AlH2O4 plus OH2 and the whole complex is plus. Okay, the whole complex is plus. So this is how it keeps getting converted until you get hexa-aquo aluminium ion. Now hexa means 6. Aquo meaning your water, H2O. Aluminium is given by Al and it is a 2 plus ion. This is what is called as hexa-co aluminium ion. So this is what is your complex and this is what helps in the neutralization of your acid. Okay. So this H3O plus, you must be thinking now acid means it is HCl, that is what we studied. So where did this H3O plus come from? H3O plus comes from the hydrogen ion which reacts with water, that is your H2O, to give you your H3O plus, and this is present in the stomach. So this is what is called by acid neutralization by your aluminium hydroxide. Moving on, we look into the preparation of your aluminium hydroxide gel. So when a hot solution of potassium alum is added slowly to a hot solution of sodium carbonate, that is at 70 degrees centigrade, aluminium hydroxide is produced. Okay. Now, potassium alum is also called as potash alum. Okay. Potash alum is nothing but the formula here you can see K2SO4 dot Al2SO4 thrice. This whole thing is called as potash alum. So when a hot solution of potash alum is added to a hot solution of sodium carbonate, you get your aluminium hydroxide as a precipitate along with byproducts, that is your sodium sulfate, potassium sulfate and carbon dioxide. Okay. Now this you should very well remember very carefully, okay? Hot solution of potash alum is only added into the hot solution of sodium carbonate. It is not added vice versa, okay? By adding vice versa, by adding vice versa, what happens is there is a precipitate of an alkali sulfate which is formed and it is difficult to wash it. So that is why you have to add a hot solution of potash alum into your sodium carbonate. So once this is done, to the filtrate, you're going to add clear solution of alum, only alum, that is your aluminium salt, chloride or sulfate with constant stirring. Once you add that, you're going to add more of water and remove all the gas. So we saw the byproduct, right? Carbon dioxide is being released. So to remove all the gas, you will still keep on adding more of water. So the aluminium hydroxide, which has precipitated out, you are going to collect it, wash and suspend in sufficient purified water. Okay, so it is hygroscopic in nature, that is it absorbs the water from the atmosphere. So you just want to suspend it in purified water so that it does not decompose or deteriorate. Okay, so this is how aluminium hydroxide gel is prepared. So once it is prepared, you need to purify. So how are you going to purify? The precipitate is washed thoroughly with hot water. Okay, keep in mind you are not going to boil it. You are just going to wash it with hot water until it is free from sulfate ion. Okay, I think the meeting will get disconnected now. I'll just send you another link. Please join to it very quickly.